Welcome to Chapter 4 of the Deep Learning Fundamentals series. In this chapter, we tackle two critical challenges in training deep neural networks: preventing overfitting through regularization and finding optimal parameters efficiently through advanced optimization algorithms. You'll learn about the bias-variance trade-off, L1 and L2 regularization, dropout, batch normalization, and modern optimizers like Atom. These techniques are essential for building models that generalize well to unseen data and train reliably in practice. Understanding overfitting and underfitting is fundamental to building good models. Overfitting occurs when a model memorizes the training data, capturing noise rather than true patterns. This results in high variance, excellent training performance, but poor generalization to new data. Underfitting is the opposite problem, where the model is too simple to capture the underlying patterns, resulting in high bias and poor performance on both training and test data. The bias-variance trade-off formalizes this. Total error equals bias squared plus variance plus irreducible error. Our goal is to find the sweet spot between model complexity and generalization, minimizing total error by balancing bias and variance. Regularization adds a penalty term to the loss function to discourage overly complex models. L1 regularization, also known as lasso, adds lambda times the sum of absolute weight values to the loss. Its key property is that it promotes sparsity by driving many weights exactly to zero, effectively performing feature selection. L2 regularization, known as ridge, adds lambda times the sum of squared weights. Instead of zeroing out weights, L2 shrinks all weights smoothly toward zero, preventing any single weight from becoming too large. The hyperparameter lambda controls the strength of regularization. Too small, and it has no effect; too large, and it underfits. In practice, L2 regularization is more commonly used in deep learning because smooth weight decay works well with gradient-based optimization. Dropout is a powerful regularization technique specifically designed for neural networks. During training, dropout randomly sets a fraction of neuron outputs to zero at each forward pass, with typical dropout rates between 0.2 and 0.5. This forces the network to learn redundant representations because no single neuron can be relied upon to always be present. The effect is similar to training an ensemble of many different subnetworks and averaging their predictions. At inference time, all neurons are active. Modern frameworks use inverted dropout. Activations are divided by the keep probability during training, so inference needs no rescaling and the expected output magnitude already matches. This ensures the expected output magnitude remains consistent between training and inference. Dropout is particularly effective in fully connected layers, where co-adaptation of neurons is most likely. Batch normalization was originally motivated by internal covariate shift, the idea that the distribution of layer inputs keeps shifting as earlier layers update. Later work suggests the bigger effect is that it smooths the optimization landscape, but either way the practical result is more stable training. For each mini-batch, batch normalization normalizes the activations to have zero mean and unit variance. It then applies two learnable parameters, gamma for scaling and beta for shifting, allowing the network to recover any representation that is optimal. This stabilizes training, allows higher learning rates, and often reduces the need for other regularization techniques like dropout. A related technique is layer normalization, which normalizes across features rather than across the batch. Layer normalization is preferred for recurrent neural networks and transformers because it does not depend on batch size and works consistently during both training and inference. Standard gradient descent uses the same learning rate for all parameters, but some parameters may need larger or smaller updates. AdaGrad, short for adaptive gradient, solves this by maintaining a running sum of squared gradients for each parameter and dividing the learning rate by the square root of this accumulated sum. Parameters with large gradients get smaller effective learning rates, and vice versa. However, A-to-grad has a fundamental flaw. The accumulated sum only grows, causing the effective learning rate to monotonically decrease and eventually become vanishingly small. RM-SPROP fixes this by replacing the running sum with an exponential moving average of squared gradients. This means the denominator reflects recent gradient magnitudes rather than the entire history, keeping the effective learning rate adaptive throughout training. ADAM, short for adaptive moment estimation, combines the best ideas from momentum and RM-SPROP into a single algorithm. It maintains two moving averages: the first moment, which is the mean of gradients like momentum, and the second moment, which is the mean of squared gradients like RM-SPROP. The first moment provides direction with smoothing, while the second moment provides per-parameter adaptive learning rates. A crucial detail is bias correction. Since both moving averages are initialized at 0, they are biased toward 0 in early training steps. ADAM applies correction factors to counteract this initialization bias. The default hyperparameters of learning rate 0.001, beta 1 of 0.9, and beta 2 of 0.999 work well across a wide range of problems, making ADAM the most popular optimizer in deep learning today. Even with adaptive optimizers like ADAM, the overall learning rate significantly impacts training quality. Learning rate scheduling adjusts the learning rate during training to get the best of both worlds: fast early progress and precise final convergence. Step decay reduces the learning rate by a fixed factor at predetermined epochs, such as having it every 30 epochs. Cosine annealing smoothly decreases the learning rate following a cosine curve from the initial value down to near 0, which often produces better results than sharp step changes. Warm-up strategies start with a very small learning rate and gradually increase it during the first few epochs, which is especially important for transformers and when using large batch sizes. These scheduling strategies can be combined, for example using warm-up followed by cosine annealing. In practice, the best results come from combining multiple regularization and optimization techniques together. A typical modern deep learning recipe might use the ADAM optimizer with a cosine annealing learning rate schedule, batch normalization in convolutional layers, dropout in fully connected layers, and L2 weight decay applied to all learnable parameters. However, these techniques can interact in subtle ways. For example, batch normalization already provides some regularization, so heavy dropout may not be needed when batch normalization is used. The key is to start with a reasonable baseline configuration, then systematically adjust one technique at a time while monitoring validation performance. Understanding how these techniques interact is what separates effective practitioners from beginners. Let's recap what we covered in Chapter 4. Overfitting and underfitting represent the two extremes of the bias variance trade-off, and regularization techniques help find the right balance. L1 regularization promotes sparsity, while L2 regularization smoothly shrinks weights. Dropout acts as an implicit ensemble by randomly deactivating neurons during training. Batch normalization stabilizes training by normalizing layer inputs, while layer normalization is preferred for sequential models. Among optimizers, ADAM combines momentum and adaptive learning rates with bias correction, making it the default choice for most applications. Learning rate scheduling with strategies like cosine annealing and warm-up further improves training quality. In the next chapter, we'll put all of this to work in a hands-on project: building, training, and evaluating a handwritten digit classifier on the MNIST dataset.